In today's session, we will mainly focus on the best practices for deploying SDA networks. We will introduce this from three aspects. First, an overview of SD access, introducing the various components of the SD access architecture. The second part is about how to perform endpoint authentication. And finally, we will discuss how to implement policies and segmentation, which is also one of the main solutions in the SDA architecture. First, let's briefly introduce what SD access is. Cisco's SD access, abbreviated as SDA, is a campus network solution, mainly comprising Cisco DNAC, Cisco ISE, and Fabric networks. SDA provides network automation, identity-based authentication and policies, network operations support based on AI and big data technologies, and data visualization. Unlike traditional IP and VLAN-based control policies, SDA defines control policies based on user and device information. When users connect to the network and are authenticated, they are assigned a scalable group tag, SGT, and access control policies are authorized through SGT recognition. Regardless of whether our user access method is wired or wireless, in the SDA scenario, we are able to achieve policy consistency. Next, let's look at the components of SDA, Fabric roles, and some terminologies. First, let's look at the management components that make up SDA. The DNAC and ISE shown at the top of the slide here belong to the management components. DNAC provides automation and intelligent operational assurance functions for SDA. DNAC's intelligent operational assurance function is responsible for collecting information from endpoint applications, etc., and provides data visualization to help us more easily determine whether the Fabric network is healthy. Then, using DNAC's automation features, we can build an SDA environment through simple operations on DNAC's GUI page. Cisco's ISE can serve as a 3A server, providing dynamic identity authentication and policy definition for users and devices. All these belong to the management components of SDA. Next, we will introduce the Campus Fabric. Cisco SDA uses virtualization technology to virtualize the network on top of the physical network. The traditional Layer 2 and Layer 3 physical network topology is known as the underlay, which serves to achieve interconnectivity across the entire network. And then the virtual logical topology, built on top of the existing underlay, is called the overlay. Meanwhile, the Campus Fabric is composed of different roles. First, the underlay devices responsible for data transmission are called intermediary nodes, which have no special role related to virtualization and are only responsible for forwarding traffic without needing to learn routes. Then, regarding the overlay, it is composed of several important roles. To better understand the roles of each, let's first briefly describe the communication process between endpoints. First, connect a wired endpoint to the edge node. Once connected, it undergoes identity authentication and is then assigned a policy. After the endpoint obtains an IP address, the edge node uses the Lisp protocol to register the mapping information to the control plane node. The mentioned mapping information relates to which endpoints are connected to which edge nodes. Other edge nodes perform the same operation. Thus, the database in the control plane node is continuously updated, and when endpoints communicate with each other, the edge node goes to the control plane node to query the destination information, and after obtaining the mapping information of the destination endpoint, it forwards the data packets to the edge node connected to the destination endpoint. This forwarding is done using VXLAN tunnel technology. If it is to communicate with a destination outside the fabric, such as the internet, then it must connect to the external network through the border node. Now let's revisit the various roles within the Campus Fabric mentioned in the slides. The control plane node is responsible for the endpoint information management system. Similar to a simple host database managing the mapping information between endpoints and edge nodes, And here, the Lisp pub/sub mentioned is an enhanced feature of the DNAC 2.2.3 version control plane node. Its specific function will be introduced later. The border node is similar to the core layer of traditional networks. It is an entry and exit point between the SDA fabric network and the external layer 3 network. The edge node is similar to the access layer of traditional networks, responsible for connecting wired terminal devices to the fabric network. Finally, for wireless terminals, it used fabric-supported access points and wireless controllers. The information of wireless terminals is jointly managed by the WLC and control plane node. Then, regarding the wireless content in the SDA architecture, we will have a dedicated ATX session in June. You are welcome to participate. Next, we will delve deeper into the various roles in the fabric, starting with the control plane node, which is marked as the green device labeled C in the slide. The control plane node is a host tracking database. It uses the Lisp protocol to manage the entire fabric's address information and tracks which edge nodes all the endpoints are connected to. The Lisp protocol can split traditional addresses into RLOC, the routing locator, and EID, the endpoint ID, which is a mechanism that separates location and identity. Endpoint ID, after a host connects to the fabric network, it will use the Lisp protocol to map its IP, MAC, or the IP prefix introduced by the border to the current location RLOC, and then register this mapping relationship to the control plane node, thus resolving lookup requests from edge and border nodes, quickly finding the edge node connected to the destination terminal. As shown in the slide, a terminal with IP 1.2.3.4, after connecting to an edge node called FE1, Lisp will associate the host's IP and MAC address with the location information RLOC, and then log into the control plane node's database. So when other hosts through the border or other edge node devices want to access this 1.2.3.4 terminal, they can easily query from the control plane node to 1.2.3.4, currently connected under the FE1 edge node, then encapsulate and forward the data to FE1, and then FE1 will decapsulate and forward it to the 1.2.3.4 terminal. In summary, the control plane node is an endpoint information management system used to map location information. Next up is the edge node, which are the three green devices at the bottom of the slide. When terminal devices connect to FE1, they are authenticated, assigned policies, and connected to the network. The edge node is similar to the access layer of traditional networks, responsible for the access of terminal devices, and can provide first-hop services. The slide introduces several functions of the edge node. First, it can work in conjunction with Cisco ISE, responsible for the identification and authentication of endpoints. Then, as mentioned before, it can register the mapping information of IP addresses, MAC addresses, and RLOC of the terminals connected to it on the control plane node. An important point to note here is, regarding the terminal entries, for example, IPv4, it records a 32-bit subnet mask. Because when terminals move within the fabric, we need to track their exact location. This way, once every terminal connected to an edge node is registered in the control plane node's database, we can easily search for the edge node to which the destination terminal is connected. Additionally, the edge node can also provide a Layer 3 Anycast gateway for connected terminals, with each edge node being assigned an SVI interface with the same IP address. Thus, no matter which edge node your terminal connects to, the default gateway uses the same IP address, meaning that when terminals move between edge nodes, they do not need to change their default gateway. Then finally, the communication between edge nodes to which terminals are connected uses VXLAN tunneling technology. Data traffic sent from terminals to an edge node is encapsulated at the edge node and then forwarded. And upon reaching the destination edge, it is decapsulated, and the traffic is forwarded to the destination terminal. Between these two edge devices, there are of course intermediary devices, but they are only responsible for forwarding traffic and do not need to share routing information. In this way, end-to-end fast, efficient, and reliable transmission can be achieved. Finally, we introduce the border node, which are the green and orange devices in the slides. It serves as the entry and exit points for data traffic going in and out of the fabric network, and communicates with external networks using BGP. There are 3 types of border nodes, including internal border, external border, and a combination of both internal and external borders. The first type, the internal border, is responsible for connecting to known subnets outside the fabric, such as the WLC firewall, and its role is to use the BGP protocol to announce internal summarized routing entries externally, and to import known external subnets into the control plane node, and when communicating with other fabric devices, it also uses VXLAN tunneling technology and needs to handle VXLAN encapsulation and decapsulation. From a path optimization perspective, when communicating with external networks, if there are clear routes, we recommend setting up a separate internal border to differentiate paths. The second type, the external border, acts like a proxy server, responsible for connecting to unknown external networks, such as the internet, public clouds. We can announce internal summarized routing entries to the outside, but do not import unknown external routing entries. We just need to mark it when setting up Lisp. So when terminals access the external network, they first query on the control plane node, and if there are no available routing entries on the control plane node, they will look for the external border through the marker, and then the external border acts as the default gateway connecting to the outside. The third type of border combines the functions of both internal and external borders, which we won't repeat here. Additionally, when we introduce the fabric roles, starting with the DNAC 2.2.3 version, a feature called Lisp PubSub was added to the control plane node. If there is an external border in the fabric, then Lisp PubSub will automatically enable the dynamic default border functionality, which can quickly implement failover for redundancy purposes. It works like this. Lisp PubSub can dynamically monitor whether there is a default route on the external border. If there is, it will register it as the default external border automatically on itself, which is the control plane node, then allows edge nodes to dynamically direct traffic to the external border with a default route. If the external border fails, loses upstream links, or there are no default routes, it will also automatically withdraw its registration as the default external border from the control plane node's database, providing fast convergence, preventing other fabric nodes from forwarding traffic to this failed external border, and dynamically detecting other available external borders to continue forwarding traffic. This not only minimizes traffic loss, but also eliminates the need for manual IBGP configuration between external borders. One important point to note is Lisp PubSub only supports newly created fabric sites and requires that the devices run a version of iOS XE software higher than 17.6. Existing SDA sites cannot opt to upgrade to Lisp PubSub. They can only continue using the existing Lisp BGP architecture, and if they wish to use it, they must recreate the fabric site. Next, we will introduce user onboarding in SDA. When users come online, the first step is to authenticate and authorize their identities, whether in traditional networks or in the SDA architecture. The essence of user authentication and access authorization remains the same, aimed at confirming the legitimate identity information of accessing users or devices, with common identity authentication methods being username plus password or certificates. And if the user is registered on the authentication server, once the accessing user's information is confirmed, authentication is successful, and then we can grant the appropriate permissions to our accessing users. There are actually many options for authorization. For example, in the diagram, when a company employee authenticates successfully using a username and password or certificate, They are given permission to access all internal resources of the company, and if at that time there is a visitor connecting to our company's network through a personal device, when we formulate the authorization policy, we can only open up certain resources or networks that are available for public access. Next, we will introduce 3 authentication methods available in SDA networks, including 802.1x authentication for verifying user identities, MAB authentication used for verifying devices like printers, and VBox authentication for visitors. Okay, let's look at how they work one by one. 802.1x authentication is a more mainstream method, allowing for authentication of wired or wireless users through username and password. This method is also the safest. The slide on the right summarizes the overall authentication process. Initially, our devices like computers and iPads have an authentication client called a supplicant built in. When these devices connect to an 802.1x network, authentication begins. The actual authentication process is executed by an authentication server. In this case, Cisco ISE acts as the authentication server, with the network device connected to the client acting as the authenticator responsible for forwarding authentication exchanges. Once the client goes online, the authentication process is initiated, requiring the user to provide credentials, such as username, password, or certificate. These credential information is sent to the network device using the EAP protocol. Then the network device uses the radius protocol to forward the credential information received from the client to the authentication server, which is Cisco ISE. Then, ISE compares the credential information provided by the client with the information on its local database or integrated AD server to authenticate the user. If the authentication is successful, an access accept result is returned to the intermediate network device, then the port is changed to a communicable state, allowing the end user to access the network. From this authentication process, it can be seen only users who are registered on the authentication server or AD server can successfully connect to the network. Some devices within the enterprise network are unable to authenticate using a username and password, such as cameras, printers, and other devices, in which case we can use MAB authentication to complete the authentication of these devices. This is also a type of authentication based on the MAC address. The slide on the right also summarizes a general authentication process. When we define authentication templates in the SDA network, we can set the order in which authentication is invoked. If 802.1x authentication is prioritized, then we need to wait for an 802.1x timeout period before proceeding with MAB authentication. Regarding this timeout period, it can also be adjusted according to one's situation. After the 802.1x timeout, if any data packets are emitted from the terminal, the switch will set the MAC address as the user ID and then forward the information to ISE. Finally, if the target's MAC address is authenticated by ISE, access to the network will be granted. Additionally, MAB authentication requires the use of a MAC address database. Cisco ISE uses the profiling service to dynamically recognize terminal types and then builds a MAC database. Let's take a look at what the profiling service is. Now, as more and more devices connect to corporate networks, sometimes we need to understand what type of device is being introduced. At that time, we can use the dynamic detection and classification features provided by Cisco ISE's profiling service to identify the types of devices connected to the network. There are many methods for data collection used by ISE for profiling. As we can see on the left side of the slide, there are terminals entering the network such as IP phones, surveillance cameras, desktop hosts, etc. The information about these terminal types is sent to ISE through various direct or indirect methods, such as the method marked ACI DEX here. which is if the AnyConnect client is installed on the terminal, then this information is sent directly from the AnyConnect client to ISE. If the terminal is accessing the network via wired or wireless, it can combine common protocols from network devices such as DHCP or DNS to send feature-rich information captured by these protocols to ISE. Information can also be collected by setting network devices to actively probe. Once the information is collected, ISE compares it with the local terminal recognition database to determine the specific type of the terminal. Identifying devices is not the final goal. What we aim to do is classify them, so we can handle permissions uniformly for different types of devices. For instance, if we identify a terminal as an IP phone through profiling, we can then categorize it into a voice via LAN when formulating authentication and authorization, and also provide differentiated network access authorizations based on the same user using different devices. For example, when a user accesses the network through a company computer, we can grant them full access permissions. But if that employee uses a personal mobile phone to connect to the network, then we can grant them permission to access the internet. By using ISE for device asset visualization, we can simplify access control for various device types. Next, the third authentication method we introduce is for guest access. If a visitor wishes to use our company's network to access the internet or our company intranet, we can provide them with guest access permissions through the guest portal. On the DNC, administrators can easily create a guest portal page, thus saving the cost of hiring HTML developers. There are 3 methods available for guests to choose from, including hotspot, self-registration, and sponsored guest access. Hotspot is a method many stores, such as KFC and McDonald's, use, where a guest connects to the guest SSID and upon opening a browser is redirected to the guest portal page without needing to enter any user credentials and just needs to agree to the terms of use to access the internet. Self-registration is where a guest connects to the guest SSID and upon opening a browser is also redirected to the guest portal page, but the guest user must enter the required information, register their own account credentials before they can access the internet, and it also supports login with social media accounts like Facebook. If stricter control of guest access is desired, you can also require guests to fill in the email address of the person they are visiting. For example, if A visits B and A wants internet access, in addition to entering necessary information like a username, A must also enter B's email address so that B can act as a sponsor, approve A's access request upon receipt, and then notify A that they can access the internet. The last method is sponsored guest access. For example, if A visits B and A wants internet access, B can act as a sponsor, log into the company's internal sponsor portal page, enter the required information, and then create a guest account for A. Once created, the sponsor can send the credentials to A, so that guest A can use these credentials to log into the guest network. In the SDA environment, we can support up to 1 million guest accounts, and the account information can be notified via email, print, or SMS, and also supports managing guest accounts through the REST API and changing the display language of the guest portal, as well as supporting login using social media like Facebook. Okay, next we move into today's demo segment, how to prepare to enable a Fabric site. I'll switch the screen, please hold on. Today's session includes 2 demos, both about enabling Fabric sites. The first demo is an introduction to some of the preparatory work needed before enabling a site. I will show you how to create an IP pool in DNC, and then we'll take a look together at the authentication and authorization policies needed to be configured in Cisco ISE. Okay, first let's look at the DNC. The version of DNC I am using today is version 2.2.3. First, create the site hierarchy on the DNC, then discover devices, provision devices to the respective sites. Next, we also need to reserve IP addresses that will be used in the Fabric network. We click on Menu, Open Design, Network Settings, click on IP Address Pool. First, we create a large address pool at the global level, then the IP pools for branch sites are divided from this large global pool. As you can see, two 16-bit address pools have already been created. After creation at the global level, we can then reserve address pools at the branch sites, according to usage scenarios. For example, at the London site, several IP pools have already been created here. If we want to create other IP pools, we can click here on Reserve, enter the name of the IP pool, for example. To create one for wired terminal onboarding, then select from the Type drop-down menu, which has several options related to the SDA workflow. Only generic and LAN are applicable. Generally, for connecting wired and wireless terminals to Fabric, or wireless APs to Fabric, we choose generic. For LAN automation and deploying extended nodes, we can choose LAN. The other three are used for configuring NFV on ENCS. This time we need to configure an address pool for terminal onboarding, so we select generic. Then next, we divide a smaller pool from which global large pool. We select the overlay option, then set the prefix to 24 bits. Next, we enter the subnet and then the gateway and select the DHCP server and DNS server. Here, ensure that the DHCP address pool and the settings on the DNS server are all properly configured, then finally click Reserve. Thus, the LAN wire address pool is set up. After setting up the IP pool next, we integrate DNAC and ISE. Regarding this part, we will have a detailed presentation on ATX next Tuesday, May 29th, so we will skip this part for now. My demo environment already has ISE and DNAC integrated. Next, let's look at the settings on ISE regarding authentication and authorization policies. Open the ISE page. The version of ISE used is also version 3.0. ISE automatically recognizes users and devices, and then processes authentication and authorization. All the processing procedures are defined in the policy site. Click on Menu, select Policy Site. There is a default setting here. Click the right side of the large fish option. Here is a default setting. Click on the fish icon on the right to view items such as authentication policy and authorization policy. First, we confirm the authentication policy. We can see that both MAB and 802.1x authentication are already configured. For devices that require MAB authentication, whether wired or wireless, they will refer to all endpoint information in the ISE's internal DB for verification. For devices that require 802.1x authentication, whether wired or wireless, they will refer to all user ID store, which includes user information from all ISE databases. After successful authentication comes authorization. We then click to view the authorization policy. Here we can define authorization rules for users and devices, such as the first one set here, the 802.1x contractor rule under VIR. In the conditions, we have set that if wired 802.1x authentication is used and the user belongs to the contractor group in the user identity group in ISE, then the result is set to assign an infra profile and to place them in a security group called contractor. The profile defines macro segmentation used in the Fabric environment, which includes information associated with a virtual network, VN. Then, the security group in ISE is equivalent to the scalable group in DNAC. So simply put, after successful 802.1x authentication, it is like assigning a VN ID and an SGT tag to the user. Additionally, as we have introduced in the PPT, ISE uses the profiling service to dynamically identify devices and classify them, so we also need to check under Administration in the Deployment section and select this ISE device. there is an option to enable profiling service, which we must ensure is activated. And it's not just for Cisco products. Other companies' products are also recognizable. And if they are not recognizable, we can also add new policies to define the conditions for recognition. All right, that concludes the first demo, where we demonstrated how to create an IP pool on DNAC, then confirmed the authentication and authorization configured in ISE, and the profiling service used for collecting device information. Next, we return to the PPT to continue with the content. I'll switch the screen. Next, let's look at segmentation in the Cisco SD Access solution. In traditional networks, we typically segment users through VLANs, and policy deployment is also based on VLANs or IP addresses. But in our SDA architecture, for security reasons, we also need to logically separate or isolate overlay subnets or user groups or specific devices, so in the SDA Fabric network, there are also two levels of segmentation: macro segmentation and micro segmentation. Next, let's discuss these two types of segmentation in detail. Firstly, macro segmentation. What we see in this diagram as individual VNs, virtual networks, is actually macro segmentation, which is a logical segmentation at the routing table level. Similar to what we talk about in traditional networks with MPLS VPNs, each VN has its own VRF routing table. We can create multiple VNs according to our actual needs, and each VN is completely isolated from the others, but within the same VN, all terminals can normally communicate by default. When a Fabric node encapsulates traffic, it tags it with a VN ID to identify the VN, and then forwards the traffic. Next, let's introduce the Fabric Zone, which is also a new feature added in version 2.2.3. What is a Fabric Zone? A Fabric Zone can flexibly allocate and map the VNs to be called at the Fabric edge, and the IPs within the VN are also selectable. With a Fabric Zone, we can divide a large-scale network deployment into smaller logical groups and manage them separately. A Fabric Zone can only contain Fabric edge nodes and extension nodes. By default, a Fabric site does not create a Fabric Zone, but even if a site does not have a Fabric Zone now, it can be added later. We can create Fabric Zones at the building level or at the floor level within a Fabric site. If created at the building level, then all floors within the building will become part of the Fabric Zone. In the example in this diagram, we can see some Fabric edge nodes are divided into Fabric Zone 1, some are divided into Fabric Zone 2. Each Fabric Zone then contains different VNs. At the same time, according to the needs of the network design, a Fabric Zone can inherit all IP pools from the VNs and control access between them. This capability allows for a more segmented and secure network architecture. With each VN operating in isolation, we can ensure that data flows only where it is meant to. This segmentation plays a crucial role in containing potential security breaches. By segregating network traffic in this manner, we effectively enhance the overall security posture. Each Fabric Zone can be tailored to meet specific security and operational requirements, providing flexible and dynamic network management capabilities. You can also use only specific IP pools within a VN. For example, in this case, Fabric Zone 1 contains 2 subnets from VN Campus, while Fabric Zone 2 contains only 1 subnet from VN Campus. And we can see both Fabric Zones. Although both use VN Campus, they use different subnets. Then, in the bottom right corner, the Fabric Edge node, it does not belong to any Fabric Zone, so this edge device can access all VNs and all IP pools in the database. What are the benefits of using Fabric Zones in SDA? First, it can limit the VN IP pool to a specific group of Fabric edges, providing flexible and refined control over the IP pool allocation on edge devices. And because some C9000 devices do not support large-scale VNs, as a cost-saving measure, we can place edge devices that do not support a large number of VNs into specific fabric edges, and then only add the number of VNs supported by the devices. Next, let's talk about microsegmentation, also known as SGT, Scalable Group Tag. We've mentioned before that in fabric networks, VNs are isolated from each other and cannot communicate, but within the same VN, all endpoints can normally communicate by default. If we want more refined control at this point, we can achieve this by creating SG-ACLs within the VN. It's somewhat similar to the traditional ACL functionality, but managing thousands of IP-based ACL entries in large networks is a burden for our administrators, and the scalability of ACLs isn't that great. However, in SDA networks, our user endpoints need to be linked to a specific user group, and then the user group is assigned the appropriate SGT label. Then, when setting policies, access control is implemented by specifying source and destination SGT labels. During actual communication, when terminal devices connect to the network for authentication, it is determined which group the user belongs to, and then it initiates. And the traffic it initiates will carry this SGT label. Thus, other edge or border nodes, based on the SGT label in the data, can refer to the local SG-ACL for communication control. Alright, let's take a look at the policy control process in the SDA environment through this slide. Based on the SGT label in the data, local SG-ACLs can enforce communication control. Okay, next, let's take a look at this slide to see the policy control process in an SDA environment. In the SDA environment, we can define policies on DNAC, and these policies are synchronized to Cisco ISE via REST API, then ISE distributes them to network devices. Alternatively, policies can be defined directly on ISE. The policies we define on DNAC and ISE are visualized as a spreadsheet, like the table in the bottom right of the slide, based on an SGT from source to destination, with source in the vertical and destination in the horizontal. We can see that communication from employee to contractor is defined as deny all, and from contractor to employee is also deny all, but communication between employees is permit all. When a user connects to the network, they are authenticated and then tagged with an SGT. In this example from the slide, the user in the bottom left connects to the network, and after successful authentication through their credentials, they are authorized and assigned to the employee user group, then tagged with SGT5. At the same time, the edge device directly connected to the employee will download the SG-ACA related to the employee user group access rights from ISE. The same is true for the user on the right, who after successful online authentication is assigned to the contractor group, then tagged with SGT10, and the directly connected edge node will also preemptively download the SG-ACL related to contractor access rights. When an employee sends a packet to a contractor, the originating edge node will also tag the packet with SGT5 and then encapsulate it for transmission. Upon reaching the destination device connected to the edge node, the SG-ACL policy is enforced. Note: the implementation of the policy occurs at the exit of the destination fabric edge. We've already confirmed from employee to contractor it is defined as deny all, so the packet sent by the employee to the contractor will be discarded at the exit of the destination edge. Thus, we can see, since these policies are based on groups and are independent of addresses, it offers a higher level of flexibility and security. This group-based approach facilitates the management and application of security policies, making it easier for administrators to maintain the network. In conclusion, so these strategies can be applied anywhere in the fabric network, thereby maintaining consistency across the entire enterprise's policies. Okay, next we'll move into the second demo session, continuing to demonstrate how to enable fabric sites I'll switch the screen, please wait. In the second demo, we'll discuss how to enable fabric sites. We'll show how to create a fabric site, fabric zone, transit for peer network, and how to add devices to the fabric, select roles, and then demonstrate how to create a virtual network and how to associate an IP pool with a virtual network. First, how to create a fabric site and a fabric zone. Creating a fabric site has a prerequisite that the site's IPDT IP device checking must be enabled, which is in the Design, Network Setting, Telemetry section, where monitoring weird clients. This setting must be active for us to create a fabric site. Okay, next we click on the Settings menu, Provision, then SD Access. Click on Fabric Site, choose from the workflow Create Fabric Site. Let's create it together. From the left side, we'll add the London site to the fabric. Click Next. During this process, if we want to create a fabric zone, we can choose Yes, which lets us select an area, building, or floor as a fabric zone. Here I want to create 2 fabric zones. We choose Site 1 and Site 2, then click Next. Finally, if the summary page is correct, click Create. So when we created the fabric zone earlier, if we chose No, and then later decided to add more, that is also possible to append. Okay, our fabric site and fabric zone are now created. Next, we need to create a transit for peer network, which is used when interconnecting the fabric with external networks. We click Create Transit for Peer Network and then click again. On this page, Transit Peer Network Type, we can see there are 2 types, SDA Access and IP Base. SDA Access is generally used for distributed fabric sites. For example, if a company has 2 fabric sites and wants to interconnect these 2 sites, this type can be selected. Its advantage is the use of Lisp VXLAN encapsulation technology, connecting the 2 fabric sites together, and the packets will carry VNID and SGT, maintaining an end-to-end policy plane. If choosing SDA access, it's further divided into Lisp-P BGP and Lisp-P PubSub. As I mentioned in the PPT, Lisp-P PubSub is an enhanced feature for DNSC 2.2.3 for control plane nodes, currently recommended by Cisco. It uses the dynamic default boundary feature, dynamically identifying available external borders with default routes. And when such an external border fails, it automatically searches for other available external borders, enabling quick failover implementation, achieving redundancy. Lisp BGP is a traditional SDA control plane architecture retained for backward compatibility. We'll discuss this later. When adding a control plane node, we'll see the same selection screen. If we choose SDA Access Lisp PubSub here, then later when setting up the control plane node, we should also select Lisp PubSub, keeping the settings consistent. Then on the right side, the IP base is usually used to connect the fabric to shared services or external traditional networks. Here, packets from the fabric VXLAN are decapsulated to local IP, are then routed using conventional routing and switching methods. Afterwards, we will use the traditional routing exchange to forward traffic. We'll select a site for this, choosing IP base, then setting a name with routing protocol as BGP, then setting 1, OK, finally save. This way, the transit for peer network is set up. Next, we continue to configure the virtual network. We click on the Virtual Network tab above, then from the workflow below, click SDA Create Layer 3 Virtual Network. On this page, if we want to add several VNs, just enter the number of VNs. I'm adding 1, write 1, then Next, and give the VN a name, such as Campus VN. Click Next. Next is assigning the VN to a site. We choose the recently created London site, then click Next. Now on this page, you see, is a new option in DNC 2.2.3. When this VN connects with the Fabric external network, we need to select an exit for the traffic. Default is to allow traffic to pass through the local external border, But if this VN is associated with multiple fabric sites and there is no local external border, then here we can also configure traffic to exit from a specified remote fabric site's external border, so I will choose the default option, click Next. Okay, finally confirm the summary page has no issues, click Next, click Create, Deploy. Okay, so we have successfully created the VN and assigned it to the site. We click on View All Virtual Networks to check. We can see the VN we just created, and it has been assigned to the London site. For other VNs, we can also add them to the site by clicking on the action on the right. Good. Now our site has 2 VNs. Associated with 2 VNs, Campus VN and Info VN. Next, we continue to assign roles to network devices in DNAC and add them to the fabric. We click on the fabric site above, click this fabric site, click London before setting fabric roles. One thing to note is that we must have the site's IPDT, the IP device tracking setting introduced earlier, must be active. Then perform provision device. Assign all devices to the site, if only assigned to the site without provisioning. Or if provisioning without active IPDT settings is not possible, then it will not be possible to add devices to the fabric. We want to set this device named border. Here we first make its control plane active. Okay, when we set transit for peer network earlier, we said if SD access list pub sub is chosen, then these 2 position settings must be consistent. But we chose IP base earlier actually. Whichever we choose here has no effect on IP base. It's just that Cisco recommends using list pub sub. Here I am using list pub sub. Click Append. Return to the previous page. I want this device to be both control plan and border. So continue to enable border role, then enable layer 3 handoff. The autonomous number defaults are fine, and below there are 2 options. These 2 options are related to setting this border as internal or external. Default is both options checked, which is external border, acting as a gateway for all positional traffic, not importing web routes. If you want to set it as internal border, just uncheck both boxes. It becomes an internal border. Acting as a gateway for known traffic can import known external routes. If you want to set it as a mix of internal and external border, then only check the top option. Leave the bottom one unchecked, then continue clicking A's transit peer site. Choose the IP transit project we set earlier, utilizing it to interconnect with the fabric external network, then click as external interface. When my environment connects to the fabric outside, the interface used is 1-022. I'll just select 1-022. This completes the setup of the external interface. Next, we'll configure additional settings within the network. By selecting the appropriate settings, we ensure seamless network integration. This concludes the main setup for our fabric site and associated configurations. Then select the VN for the routes to be advertised externally and allocate VLANs for them. I'll advertise these 2 VNs, then set the VLAN numbers. Okay, finally click Save. Return to the previous page. If connecting to the fabric external network and you're using a multi-column route, you can also click Add on the right to continue adding other external interfaces. And at the bottom, there's an option to select an IP pool. Here I choose L3 handoff. The IP pool selected here is used for automatic IP routing between the border node and IP peer. Then finally click Add again, finally deploy, apply immediately. Thus the device turns blue, since it's both a control plane node and a border, so it displays as CB. And before setting up the edge node, we need to set an authentication template for endpoint onboarding at the London site. We click on Host Onboarding, then here select the highest security level of closed authentication, then choose Deploy. Okay, this sets up the template for endpoint onboarding. We continue setting up the edge node. Since we enabled the fabric zone, we click View Site Hierarchy, then click on the first Site 1, this fabric zone. Enter here to set up the edge node. We click on the device edge 1, then enable edge. Click Append. Deploy. Okay, we've added the edge devices in this fabric zone to the fabric. Similarly, we need to set a host onboarding template for user onboarding. Choose Closed Authentication. Okay, that sets up the first fabric zone. We then select another fabric zone, Site 2 for the same settings. Enable Edge. Okay, this edge device is also added to the fabric. And similarly, set up the host onboarding template. Okay, now in this fabric, a border and a control plane node have been set up, and in the two fabric zones, an edge node has been set up. Next, we configure the Anycast gateway for the site's VN, linking the previously reserved IP pool to this VN. We click on Provision SD Access, then enter this virtual network. We can see the campus VN we set up, and the two default VNs. We click on Create Anycast Gateway, select the VNs we want to associate. We choose Campus VN and Infra VN, click Next. Okay, first setup for Campus VN. Then from the IP pool, select the reserved addresses to link to the VN. First, we choose for wireless endpoints onboarding, our endpoint wireless IP pool, then name the VLAN, such as wireless. We can also click the option below to auto-generate a VLAN name, then select data for traffic type. There's also an option for scalable group. If we set up terminals to onboard without authentication, we can define SGT here, but if it's 802.1x or MAB authentication, ISE will dynamically assign SGT, so no need to configure here for wireless endpoints onboarding. Thus on the right side, this wireless box must be active, and within a VN, multiple IP pools can be associated. I'll add another IP pool, click the plus sign on the right, to associate another for wired endpoints onboarding, named LAN wired, name it wired, and select data for traffic type. Okay, no other settings needed, okay? Then set up the left side for Infra VN. This Infra VN is usually used for wireless AP extension nodes onboarding. As an underlying infrastructure, we can select the AP used address pool from the IP pool, then choose AP for pool type, enter a VLAN name, choose AP, set it as AP, then click Next, check the summary. If no issues, next finally submit. This way, at the global level, the campus VN at the fabric site is associated with two IP pools, and the Infra VN is also associated with an IP pool for wireless APs. This process takes a little time. Please wait a moment. Next, continue to assign VN and IP pool to the fabric zone, since we know the fabric zone also acts as a layer 3 isolation. Okay, settings are done. We proceed to the fabric zone page. We click on the global in the upper left corner. Then navigate to the appropriate section to finalize the configurations and ensure all settings are correctly applied to maintain network integrity. Then we enter into Fabric Zone Site 1, select, then add a Layer 3 VN. We add two VNs inside Site 1, click Update. Next, choose which IP pools to use within the VNs, such as this Campus VN. I select Create Anycast Gateway from the Action menu. I choose an IP pool for wireless use, then click Append, and for Infra VN, I also select an IP pool. Choose AP, click Append. Okay, that sets up one fabric zone. We now set up another. Click on this fabric site, set up another fabric zone. Also choose to append a Layer 3 VN. This time we add one VN, Campus VN, then click Update. And when associating IP pools, this time we associate the VR IP pool. Select Append. Okay, this sets up the VNs and IP pools for both fabric zones. We can see that when setting up fabric zones, we can pull different VNs from the fabric site's VNs and also choose different IP pools from the VNs. Next, we still have configurations to do for host onboarding, then set up ports for host onboarding, create scalable groups, define group-based policies, and finally test this fabric. This part was demonstrated in the April 19th session about network segmentation. You can check the replay. Today's second demo ends here. We've introduced how to enable fabric sites, such as creating fabric site, fabric zone, virtual network, and how to add devices to the fabric, select roles, etc. Finally, we'll go back to the PPT to review today's content. I'll switch the screen. Please wait. Let's review today's key points. Firstly, when deploying SDA architecture, follow Cisco's SDA deployment best practices, plan reserved IP addresses for fabric sites in advance, IP pools, and set up authentication and authorization policies on ISE. Furthermore, we can use a combination of DNAC and ISE to centrally manage policies. Whether for wired or wireless networks, we can define policies based on VN and SGT on DNAC, then deploy them to network devices through ISE. Thus, we no longer need to define ACLs on each device. That's all for today. Now we return control to the host. Thank you to our Cisco Enterprise Network expert, Su-Ying, for the excellent explanation and demonstration. Next, we move to the Q&A session. You are welcome to ask questions in the Q&A panel. Be sure to send to all panelists. While you prepare your questions, let me briefly introduce our survey to get your feedback, to better assist you in future events. We've prepared a few questions. Please scan the QR code on the screen to respond. It will take about 1.5 minutes. After the meeting, we'll send the materials shared today to your provided contact information. Also, the recording of the meeting will be sent to your email. After all ATX sessions end this month. So please provide a valid email address. We have some typical questions that many of you encounter. We'll have our experts answer them here. The first question is, does the SD Access environment support third-party Redis servers? Besides Cisco ISE, please answer. Okay, I'll answer. That is not possible. SD Access does not support third-party Redis servers. Only Cisco ISE is supported. Okay, thank you. Okay, thank you. The second question is, what licenses are required for Cisco SD Access? Network devices require a DNA Advantage license, and for ISE, because SD Access uses features like PS Grid and profiling for device recognition, a Plus license is needed. Okay, thank you. Thank you for the expert's answer. Due to time constraints, we will not continue answering. If you have further questions, please continue to ask in the Q&A panel. As we wrap up today's session, I'd like to remind everyone to fill out the feedback survey. Your responses are crucial for improving future webinars. Thank you all for attending, and we hope to see you at our next event. Regarding the content introduced today, we have prepared some documents, hoping to help everyone better learn and utilize SD Access. I'll first post the link in the chat window. That concludes today's expert seminar on deploying best practices for SD Access. On May 24th, which is next Tuesday at the same time, we have prepared another session on the SD Access architecture for you, focusing on migration strategies and best practices for SD Access. You are all welcome to join. Our expert seminar concludes here today. Thank you for your participation. And thanks to our expert team today for the insightful presentation. Have a pleasant day, and we'll see you next Tuesday at the same time. Thank you.